Hi guys, welcome to today's tutorial. Today we're going to solve question 2, 3 and 4 of tutorial sheet 8, which is in static equilibrium. Okay, so question 2 is here. It reads, for the equilibrium situation shown in the figure. So the figure is this one here. So for the equilibrium situation shown in the figure, find W3 and W2. Assume that W1 is 800 newtons and that the pulleys are frictionless so that they do not change the tension in the cords. Okay, so we have this system here. Now this system, if we redraw it, we'll end up with not good with drawing. I am very bad at it, in fact. We have okay, so we have a mass there, and we had another mass here, where this was W3, W2, and W1. Okay, now these are acting at 40, and this is acting at 50 degrees. So this is the information that we have, or this is the system that we have. Now we've been told that we can assume or take W1 to be equal to 800 newtons. Okay. Now if we take W1 to be equal to 800 newtons, meaning we're here, so we can look at we can focus on the pulley here. Okay. If we focus on this pulley, there are two forces that are acting on this. There's the weight, okay, which is W1, and there's the tension, which is tension 1. So we are having two of them acting, and if this is in equilibrium, we can say that W1 is equal to T1. Alright, that is why it is in equilibrium, it is not moving. If at all that was not the case, the system would not be in equilibrium. You would find this would either move down or move up. Okay, the fact that it is not moving, meaning T1 is equal to W1. So we can say that T1 is equal to W1 or weight 1, which is equal to 800 newtons. Right? Now, if T1 is equal to 800 newtons, and we've been asked to find W2 and W3, how do we go about it? Okay, we know that the tension, the force that is in this tension, is not acting horizontally or vertically. The same with tension 2. Okay, they are acting at angles. So we are going to have to find the vertical component of the tension here and the vertical component of this tension, the horizontal component of this tension, and the horizontal component of this tension. Okay, personally, I like to work with the x-axis. Okay, I don't know, I've liked working with the x-axis since way back. It is easier for me to make calculations. So if you are okay with working with the y-axis, when finding the components, you can work with the y-axis, where you're going to be using 40 degrees and 50 degrees for tension 2. But personally, I like to use the angle with reference to the x-axis. So the angle with reference to the x-axis here is going to be 50 degrees, whilst the angle here with the reference to the x-axis is going to be 40 degrees. Okay, so if I am finding the components of T1 with reference to this angle, I can say, so I can start with T1 components. Okay, T1 components will have the x component is going to be equal to T1 cos 50 degrees. Okay, because I'm using this 50 here. Then the y component is going to be equal to T1 sine 50 degrees. Okay, the T1 components. Then we can also find the T2 components. Okay, T2 components, the x will be equal to T2 cos 40 degrees. The y component will be T2 sine 40 degrees. Okay, that's what we have. So T1, if we have these components, the T1 components and the T2 components, okay, we have that, and the system is said to be in equilibrium. Okay, now we know from the conditions for equilibrium that if the system is in equilibrium, then the summation of forces is equal to 0, or the net force is equal to 0. The net torque is equal to 0. All right. So that tells us that the summation of the components of these forces in the x-axis is going to be equal to 0. All right. And then the summation of the forces in the y-axis is also going to be equal to 0. Okay, so what we have in the x-axis is that T1 cos 50 will be equal to T2 cos 40. Okay, and in the y-axis we'll have T1 sine 50 plus T2 sine 50. Okay, I'm going to have to hold on to this for now. Okay, because the reason why I've added this instead of saying equal to is because of the fact that if you look at our graph, the tension in the T2 and T1 are having vertical components that are pointing in the same direction, right? If you remember from the last video that I posted, we look at the direction. So this, if we agree, if we say that this, the top is going to be positive, whilst the bottom is going to be negative, and the right will be positive, and then the left will be negative, then we are going to have the vertical components being in the same direction, hence having the same sign. Okay, so they will be positive. Now, what is going to be negative? What components or what forces are going to be balancing with the positive components of the tension? If you look at it, just here, we've got this force here, the weight. If we we consider this point as our reference point, we find that the forces that are acting on this is the tension 2, tension 1, and this weight here. So meaning that the vertical components of these tensions are balancing with this weight so that it is not moving. In short, so that it is in equilibrium. Okay, so meaning that these two will be equal to this weight. So we can say here that T1 sine 50 plus T2 sine 50, we have sine 50, no, this is supposed to be 40. Okay, 40 is going to be equal to weight 2. Take note, I did not include weight 3 because weight 3 is going to be taken with reference to this point. We are just focusing on this point here. So we should just look at the forces that are acting on this point. And that's T1, T2, and W2. Okay, that's what we have. So having this can help us to find the values that we want. We know that T1 is equal to 800. Okay, so we can say 800 cos 50 plus T2 cos, is equal to, this is equals to T2 cos 40. So what is T2? T2 is going to be equal to 514.23, because if you find 800 cos 50 will give you 514.23 divided by cos 40. Okay, if you find that, you're going to find that T2 is going to be simplified as 671.28 Newton. Okay, so we found T2. Now, T2 is the tension here. That's what we have. Okay, and this T2 is going to help us to find W. Okay, we can use T2 to find W2. Okay, how do we find W2? All right, so we have found T2. Now we want to find W2. Okay, using this side of the equation for the summations of forces in the y-axis, we have T2 being equal to, here we have T1 being equal to 800 sine 50 plus T2 we have found as 671.28. So this will be multiplied by sine 40, and that will give us W2. Okay, since we want to find W2. So what is W2? W2, if you simplify this equation, W2 will be equal to 612.84, okay, which is 800, okay, plus 431.49, okay, and once you add this, you're going to end up with 1044. This is W2. And W2 is what we have in our drawing. W2 is here. So we found W2, but the question has asked us to find the W2 and W3. How do we find W3? Now, looking at this diagram, we have got this point of reference. And on this point, on this pulley, we have got two forces acting on this pulley. We've got the weight 3 and the tension. And like I said with a reference to this one, if at all this is in equilibrium, meaning that these two forces are in equilibrium, they are balancing up. Okay, so that means that the force that is W2 is going to be equal to the force which is in tension 2. Now, remember we've already calculated tension 2. Tension 2 is equal to W3, and since we have calculated tension 2, we'll take this as W3. So we'll say T2 is equal to W3, which is equal to 671.28 newtons. Okay, that's what we have there. Of course, I know I've noticed that this answer is a bit different from the one that's been given as the solution for a tutorial. I'm not sure where I have made a mistake for me to get this answer. It's slightly over. So it could be that maybe with my calculations as I was punching on the calculator, I've made a mistake here and there. But the process of getting to the answer is the same. So if you follow this, that's how you're going to go about solving question 2 of this tutorial sheet. Okay, so now we can go to question 3. If you have questions on this part of the question of the tutorial sheet, you can always ask them in the comment section, or you can find out from the class rep my contacts, and then we can of course go through them. Mind you, these problems in physics, per se. You can look at the textbooks such as college physics, look at CWA. You'll find that there are a lot of solved problems that will be guiding you on how to go about this step by step, so that in case you've got challenges here and there, it will be of help, not just because of the not just for the questions that are in your tutorial sheet, but similar questions that can help you to prepare for your exams as well. Okay, so let's go to question 3. This is our question 3. So it reads, the uniform 120 Newton board is supported by 2 ropes. So we've got 2 ropes as shown. Okay, a 400 Newton weight is suspended 1/4 of the way from the left. So from here to here, we've got 0.25 L. That's what we have. Then find the angle theta. We're looking at this angle theta here, made by the left rope, and FT1 is here, and FT2. Okay, so we have got the task of finding the angle theta, FT21 and this is FT2, this is FT1. Okay, that's what we have here. So if you look at this diagram, it's a bit different from the two questions that we've solved so far. It if you take note, you know there's a possibility of rotation here. This question is a question that will require us to find a torque at some point. Okay, remember from the conditions of equilibrium, the two conditions of equilibrium are that the forces, the net force should be equal to 0 and the net torque is equal to 0. And if you take note, in the two questions that we had just solved, we have not used torque at all in any of these two. We just focused on the net force. Like I said in the previous video, sometimes you can use all the conditions, as in both of the conditions, but in some cases you can only use one. Where if you're using one, you would have to talk about the forces in the components, like on the x-axis and in the y-axis. Okay, but this question has come with a different challenge. We are going to have to include the torque as well. Okay, so remove this. We have question 3. Okay, yeah, question 3. So the diagram we had a uniform board, okay, and it was said to be 120 newtons. So it is being supported by these ropes, and the ropes have got angles. There's theta here, and there's another rope here. It is being supported at, this one is 30 degrees. This has been given to us, 30 degrees. Now there's F tension 1 and there's F tension 2. Okay, now we've been told that this board is 120 newtons long. Okay, so for uniform rods or boards, I remember talking about taking the center of mass. I'm not sure if I talked about that or I just thought of it, but you need to take you're going to have to assume that the weight is coming from the center of mass, because we know that the center of mass is where the mass of that body, of a body, seems to be concentrated. Okay, so meaning we'll take all of this rod or board to be we'll take its mass to be concentrated on the center of mass. So if we take this as center of mass, mainly it is at the center of the board. And since it is 120 newtons, so we're going to say the weight is going to be 120 newtons. Okay, now we've also been told that there's a mass which is suspended from about 0.25, we have 400 newtons being suspended from 0.25 L. Okay, because the reason why I've used L is we're going to take the length of the board as L. All right, so meaning that at 0.25 multiplied by the length of the board, we have a 400 newtons mass suspended. Okay, so that's what we have here. Now we're going to use the means that we've been using even in the previous questions to solve this particular problem. We have got, I'm going to take the forces in the y-axis. Okay, so the forces in the y-axis in this case will be the 400 Newton mass, the center of mass, which is the weight of the board, of course, and then, mind you, this rope is acting at an angle. So meaning it has got a vertical component and a horizontal component, the same with this one. So the vertical component of this tension is the one that is supporting the two masses together with the one that's coming from FT1. Right, so we can say that the summation of forces in the y-axis will be equal to, like I said even in the previous question, I like working with the x-axis than the y-axis. It's easier for me. So I'm going to have to work with the angle here instead of the 30 degrees. So the angle here will be 60 degrees. And here I'm going to have to work with alpha instead of theta. All right, so the angles that we have here will be, in the y-axis, we'll have 120 newtons, okay, plus 400 newtons, giving us, I'm going to take FT1 sine 60 plus ft2 sine alpha. Okay, that's what we have there. Then what about the forces in the x-axis? So the forces in the x-axis will be, so we'll have summation of forces in the x-axis, and we'll have, if we look at our diagram, we'll simply have the force being the vertical component, sorry, the horizontal component of Ft2 and the horizontal component of Ft1. We do not have any other forces acting in the x-axis. So we'll have Ft1 cos 60 being equal to Ft2 cos alpha. That's what we have there. Now, we also, like I said, are going to look at the tension. Okay, we're going to find the tension of this board. So, meaning the net tension is going to have to be equal to 0. And to find the tension, I had to take moments about tension. Torque. Okay, this is not tension but torque. I keep mistaking the two because of the T. Alright, so if we take the tension about this point here, meaning this is out, alright, and we are going to have to focus on the forces this side. So if we take the tension about this point, we are going to have the first one, like I said, if we have clockwise tension, we are going to take, clockwise torque. Okay, clockwise torque will take it as negative, and anti-clockwise torque will take it as positive. Of course, you can change with your preference. If you want this to be negative, you can make it negative. If you want this to be positive, you can make it positive, depending on what you're comfortable with. So the torque will be equal to 0.25 L multiplied by 400 newtons. Of course, because it is in the clockwise direction, we are going to take that as negative. So we have negative 0.25 L multiplied by 400. Okay. Then we'll have minus 0.5. Mind you, it's at the center of mass. I said it usually we take the middle or the central part of the object as the center of mass. So since this is going to be halfway, that will be 0.5. So 0.5 L multiplied by 120 newtons. Okay, then that will be, so this is still in the same direction. But then if you look at the force here, okay, the vertical component of tension 1 is going to have to make this go in the opposite direction. Right? So meaning we're talking about it being positive. So we'll have plus ft1 sine 60. Okay? And that is multiplied by L because it's at the furthest end. So that's L. Okay? That's what we have here. How do we find the total of this? Just for the torque, we'll get back to the forces just to simplify the torques. So this will give us negative 100 L minus 60 L plus ft1 sine 60 L. Alright, that's what we have. Meaning that we can find T1, can't we? Yes, we can. Or ft1. That will be ft1 sine 60 L will be equal to 160. Okay, so we've just moved this it to the other side of the equation, and if we divide, oh, this is 160L, right? So we've got L on both sides of the equation, so they will divide out, and we'll have ft1 being equal to 160 divided by sine 60. Okay, if we divide this, we are going to find ft1 to be equal to 184.75 newtons. That's what we have as our ft1. Okay, now if ft1 is equal to this, what is ft2? How do we find ft2? We go back to the summation of forces in the x-axis. The summation of forces in the x-axis gave us this. Okay, so we'll say summation of forces in the x gave us ft1 cos 60 is equal to ft2 cos alpha. Okay, so what do we have here? We're going to end up with, we have ft1, which is 184.75 cos 60 is equals to ft2 cos alpha. Okay, meaning if we simplify this, we'll find that ft2 cos alpha is going to be equal to 92.38. Okay, that's what we have for now. We still don't know what ft2 is, and we don't know what alpha is. We have got a task of finding out what alpha is. So to find alpha, we can go back to the summation of forces in the y-axis. Perhaps that will be able to help us. Okay, so we have got 400 plus 120 newtons. Okay, I can write it again. We'll have summation of forces in the y-axis will be equal to 120 newtons plus 400 newtons being equal to ft1 sine 60 plus ft2 sine alpha. That's what we have. So if we simplify this, we're going to end up with 520 newtons being equal to ft2 sine alpha plus 184.75. Okay, 184.75 sine 60. That's what we have. If we simplify this, we are going to have 520 is equal to ft2 sine alpha, okay, plus 159.998. Okay, I've left it in this term because it was going to be difficult for rounding it off to the nearest number, because we are going to have to end up with 160, and I feel this is more reliable. Okay, so what is T2? Sorry, FT2. FT2 is going to be equal to FT2 sine alpha. Sine alpha is going to be equal to 360 newtons. That's what we have. So, okay, let's let this be our equation 2 so that this can be our equation 1. Okay, the one where we found ft2, because we've got two ft2s now. ft2 cos alpha giving us this, and we have got ft2 sine alpha giving us this, so we can do that. So if we divide equation 1 into equation 2, we'll get we'll have we'll have ft2 sine alpha being equal to 360 newtons, and divide this by ft2 cos alpha, giving us 92.38. The ft2s will divide out. ft2 will divide with ft2. Sine alpha cos alpha will give us tan alpha. So we'll have tan alpha being equal to 3.897. Okay, meaning that alpha is going to be equal to tan inverse of 3.897. Okay. Now, if we simplify that, we are going to find that alpha is equal to 75.6 degrees. Now, the question asked us not to find alpha, but to find theta. Remember here, we have theta here, but I was working with alpha here. So to find theta, we're simply going to have to subtract theta from 90 degrees. Okay, so say theta is equal to 90 degrees minus alpha. So theta is going to be equal to 90 degrees minus 75.6 degrees, and theta is going to be giving us 14.4 degrees eventually. That's what we have. Okay, so now we have got theta. It is going to be easy for us to find T2. Okay, so to find T2, we can go back to, we can use any of the equations that we've come up with. One of them being ft2 is equal to 300. Okay, let's go back and check the equation that I'm using, just in case somebody has not followed it up. We had this equation here, equation 2, okay, which is ft2 sine alpha is going to be equal to 360 newtons. That's the equation that I've adopted. So using equation 2, where we can say that ft2 sine alpha is equal to 360 degrees. Okay, so we'll be able to find ft2 as 360 degrees divided by sine 75.6 degrees. Then we'll have ft2 to be equal to 371.67 newtons. So we have found ft2 here. The question asked us to find ft2, ft1, and the angle theta. We have ft2 here, we've got the angle theta here, and we found, where is the one? ft1, we found it is here. So we have found the three, we've managed to calculate the tasks that were given to calculate. Now, mind you, here, you'll notice that the angle that, ft2, I have found to be 372. That's the answer that was supposed to be here. It was supposed to be 372. This was just a typing error where they had written 360 instead of 372. Okay, so we can now go to question 4. And again, if you've got questions, ask. Okay, the questions might not even be in the tutorial sheet. They might be questions that you've encountered as you were solving individually. You can send them through and I can have a look at them and see how we can help each other. Okay, so we'll go to question 4. Question 4 reads, a uniform ladder 5 meters long weighing 200 newtons is leaning against a frictionless vertical wall with its base 3 meters from the wall. The coefficient of static friction between the bottom of the ladder and the ground is 0.45. How far, measured along the ladder, can a 200 Newton man climb before the ladder starts to slip? Okay, so there we have got a ladder. This is the ladder that is leaning against the wall, right? This is frictionless. This is frictionless, meaning it is possible that this ladder can slip depending on how much weight is pulling against it. Okay, so now what we have here is that this ladder, as it is leaning against the wall, from Newton's third law of motion, to every action there's an equal but opposite reaction, meaning the force that this ladder is exerting against the wall is the same force that the wall is exerting against it, okay, onto it. So we have got the force here. I'm going to call it, okay, let's draw the diagram here so that, I know my drawing is bad. There. Okay. So we have, that's the ladder we have. So we have this force, which is again acting on the ladder with reference to the wall. I'm going to call this F4. You can call it whatever you want. You can name it letters, A, B, C, D, whichever you want. But I want to work with F4 just to remind me. Then there's the force which is acting with reference to the ground. Okay, the force that's acting with reference to the ground. I'm going to call this G. G for ground. Okay, can make it ground. Then there's the force. This force, which is the force of friction. Okay, there's the force of friction acting against the direction of slippery of the ladder. Okay, then we've been told that this ladder is weighing the ladder is weighing 200 newtons. Okay, like I said in the previous example, we usually take the center of mass as the point of action of the weight of the ladder. So if this ladder is 5 meters, of course, we've been told it's 5 meters. So the weight of the ladder is going to be 200 newtons. Okay. Now we've also been told that there's a man who has climbed up the ladder and he's weighing 600 newtons. All right, 600 newtons. The reason why I have put the 600 Newton on top of the 200, as in further away from, much further than the 200 Newtons, is because obviously if this person is going to climb, is going to be heavier than the board itself, for it to slip, meaning that the person would have gone a greater distance from the person would have gone a distance from the center. Okay, that's what we have. Now we've been told this is 5 meters and we've been told this is 3 meters. There's an angle of action here. We've not been given that angle. Okay, so that's what we have about this ladder. Now this ladder question is a question that you're going to have to be careful with as you are solving it, because it doesn't really, it's not so complicated anyway. We'll solve it. So now we are going to work with the forces in the y-axis, the forces in the x-axis, and the tensions, of course. So in this one, we are going to have to use all the 3 equations that we can probably come up with when we're dealing with equilibrium problems. Okay, so we'll have if we look at the forces we can look at the forces in the y-axis. Yes, we can start with that. So summation of forces in the y-axis is going to be equal to, in the y-axis we've got the 600 Newton. Of course, let me put this here. We'll have this as positive and this as positive. Okay, so if this is positive and the other opposite direction is negative, then we are going to have the 2 forces as negative, whilst the force that's coming from the ground will be positive because it's pointing in the positive direction. Of course, I'm not going to write that directly. I'll just take them. I'll take them to different sides of the equation so that we'll have 600 newtons plus 200 newtons giving us the force coming from the ground. Okay. Now that means if this system is in equilibrium, then we can say that the two forces are adding up to give the force which is coming from the ground. And that means the force from the ground is going to be equal to 800 newtons. That's the force coming from the ground. Okay. Now we want to know the angle here. What's our angle here? At which angle has this ladder been placed with reference to the ground? Okay. Now if we go to trigonometry, we can use the cosine function to find the angle here, because we've got that. So we'll know that cos theta is equal to opposite over cos theta is equal to, I'm looking at SOHCAHTOA. So adjacent over hypotenuse. So we'll have the adjacent, which is 3 meters, okay, and the hypotenuse, which is 5 meters, okay. That's what we have. Meaning that theta is going to be equal to cos inverse of 3 divided by 5. And if we simplify, we're going to find that theta is going to be equal to 53.15 degrees. So that's the angle here. Okay. Now, if this is the angle here, if you go back to mathematics, we know that if this is a triangle, okay, I don't remember the exact topic where they teach this in mathematics, but if this is theta, then this is also theta, and this is also theta. This should come from some law, some principle in mathematics. I'm sorry, I don't remember the principle or the law where this comes from, but this is true. Okay, so now we go to the forces in the x-axis. Since we've talked about the forces in the y-axis, we've found the angle here, which is equal to the angle here and equal to the angle there, then we can go to the forces in the y-axis. So forces in the x-axis, we'll have forces in the x-axis will be equal to the force with reference to the wall being equal to the force of friction. The diagram we have here, there are only two forces in the x-axis, this force and this force. This one is pushing in the positive, this one is pushing in the negatives. So we've got these two. And if the system is in equilibrium, meaning the two forces are equal. Okay, so we will say that that's the situation. But we know, okay, but we know that the force of friction is equal to the constant of static friction multiplied by Fn. That's what we know. We've done this a lot of times. Okay. Now, the challenge is, how do we get Fn? We know that Fn is the force that is acting in the opposite direction with reference to the weight. Okay. The normal force, in short. So we've got two forces acting downwards. We've got the 600 Newton force and the 200 Newton force. These two are acting downwards, meaning that the normal is going to be, okay, this is going to be the normal. And if the system is going to be in equilibrium, meaning the normal force is going to be the summation of these two. Okay, so we can say that where Fn is equal to 600 plus 200. And we are going to have the force of friction being equal to mu 0.45, which is the constant that we've been given, multiplied by 800. Okay, and the force of friction is going to be 360 newtons. That's what we have. Now, what are we remaining with? We're remaining with the torque. So this torque, I tried to find the torque taking this as the reference point. So I tried to find the torque at this point, or taking this as the pivot. I got the answers, but it was more complicated and it took me longer compared to finding the torque using taking this as the point of reference. Okay, if we use this as the point of reference, we are going to have forces the tension with reference to this force, this force, this force, and this force. We'll have 4. Okay, but if we take this point as our pivot, we're only going to have the force with reference to this point, and this point. Okay, of course, in both cases, you are going to find the answer. I'll find the tension with reference to this point, and maybe, okay, in the next video, I'll find the tension with reference to this point. Okay, but for now, I'll just work with finding tension with reference to this point, because as it is, we're running out of time. Okay, so the tension, the second condition for equilibrium is that this is going to be equal to 0. Okay, so taking talk about FG, which is the ground. Okay, what we're going to have is, okay, that's what we have. So I wanted to remind people before I start taking the tensions, or the torque, before I start calculating torque, I wanted to remind you that torque is the product of the distance and a perpendicular width, the force multiplied by the perpendicular distance, or it could be a force which is being applied perpendicularly to a certain distance. Okay, meaning that what we have here is going to be a bit complicated. No. It's not going to be complicated, but we're going to have to do more work, because we'll have to find the perpendicular distances on which these forces are acting. If we look at this as our point of reference, there is this force. Okay, the distance from here to here is not perpendicular to this. The distance that is perpendicular to this force is actually this distance. So we're going to have to calculate this distance. Then the force, the 600 Newton force is also acting at a certain perpendicular distance. So we are going to have to calculate that perpendicular distance. This force with reference to the wall is acting in this direction. The force that is the distance that is perpendicular is actually this distance. So I'm going to have to calculate these distances. This distance, this distance. This distance is going to be difficult to calculate because we do not know this distance. Okay, so we are going to have to start with calculating. Let's start with calculating this distance here. To calculate this distance, we can even use Pythagoras theorem, because we have 3 meters and we've got 5 meters. We are finding this. So from Pythagoras theorem, we know that a squared plus b squared is equals to c squared. Okay, and we have a squared, which is 3 squared, plus b squared is equal to c is 5 squared. So meaning that we are going to have 25 minus 16 giving us minus 9 giving us 16. So meaning that our b is going to be equal to 4. Okay, 4 meters. So this is the value of this distance, 4 meters. Okay, now we also have to find this perpendicular distance. To find this perpendicular distance, we know that the center of mass is acting at the weight, the 200 Newton is acting at the center of this ladder, meaning the distance here is 2.5 and the distance here is 2.5. Okay, and if that's the case, then we can say we have R already. if this is 2.5 and this is 2.5, we've got the hypotenuse, which is 2.5, and we do not have this, but we've got theta here, and we are looking for this one. So we can simply just use the formula for the cos function. We're going to say r cos theta is going to be equal to x. All right, so we're looking for x. Our r is 2.5 cos 53.13, and that will give us x. So x is equal to 2.5 cos 53.13 is going to give us 1.5 meters. All right, so the distance here is 1.5. In fact, if you look at this 3 meters, meaning this one has been cut by half and this one has been cut by half, so we're having a 3 meters distance. That's the perpendicular distance that we are going to be working with. Okay, so to find the torque now, to find the torque, we're going to say since we're taking moments about this point, we'll start with this multiplied by this. Okay, so we'll have the perpendicular distance here is 1.5. Now this is, if we talk of the rotations, if I thought it is going to rotate, we are going to have this going in this direction. This force is going to be in this direction, and that is positive. So we'll have 1.5 multiplied by 200, okay, plus the other force that's acting is the 600 Newton weight, okay, and that is acting at a distance which is unknown, and that's going to help us to find the distance that we've been told to find. So x multiplied by 600, and that will be plus, we've got the other force, which is the force with reference to the wall. We already found the force with reference to the wall, isn't it? The fact that we've got the force of friction, which is equal to the force with reference to the wall, meaning that if we have force of friction, then we've also found F with reference to the wall. So we'll have the distance, the perpendicular distance we've calculated as 4 meters. So that will be 4 times 360. Okay. This plus, no, this is not going to be plus. This is negative because it is going to have to cause it to go in the other direction. Okay, so that's what we have. And if we simplify this, we're going to get 600x plus 300 300 minus 1440. Okay, that's what we have. So if we take 1440 on the other side, we are going to end up with 600x. Oh, we take this on the other side, 300 minus 1440. We are going to end up with 1140. Divide by 600, divide by 600, and x is going to be equal to 1.9 meters. Okay, now 1.9 meters is the distance from here to here. Okay, that's the distance from here to here. That's 1.9 meters. But what we actually want is not the distance from here to here, but the distance from here to here, because the question asks us to find how far the person had to climb the ladder. Okay, so we are looking for this distance here, and if that's no, what we have found is not the distance here, but the distance from, okay, it's the perpendicular distance. In short, we have found the perpendicular distance, and we are going to look for the hypotenuse. So we have got x. Okay, if we use the same formula that we used here, where we say r cos theta is equal to x, okay, we are going to have, we are looking for r. So r will be equal to x divided by, our x has been found as 1.9 divided by cos 53.13, meaning that our r is going to be equal to 3.1, it's 166, so I just round it off to 3.17 meters. Okay, so meaning that before the equilibrium is, before this system is no longer in equilibrium, the person will have to climb 3.17 meters. Obviously, that's, if you look at it, 3.7, this is 2.5, so that's like 3.2 is obviously going to be on top, approximately where I'd place the 200 Newton force. That's how far the person will climb before this ladder starts to slide. Any distance before that, it is in equilibrium. The moment it reaches that point, it's no longer in equilibrium and it's going to slide down. Okay, so in the next video, we'll do question 4. Question 5, we've done question 4. Okay, let's see if people can solve question 4. Let's do it as an assignment. Okay, question 4 will be an assignment. It will be due on Friday. Today is Wednesday. Okay, let it be due on Saturday. Okay, so question 4. Okay, question 4. Sorry, question 5. Assignment. Then due on Sunday. Sunday will be, I'm not sure about the date. Due on Sunday. So today is Wednesday, which is 18th, and Sunday you can figure out the date. That will be that. So you are going to have to send this to, send it to Nonde Elizabeth at yahoo.com. So people should send this on Sunday, before Sunday, even better, but the due date is Sunday 24 hours. If you send it afterwards, I'm not going to consider it, okay, because in the next video I'm going to have to do this question. So if you send it afterwards, then I'm going to assume you have copied from what I was solving. I want to see if people are able to solve these questions on their own. Okay, so like I said, if you've got questions, you can send them in the comment section, or you can ask through the classroom. Okay, so that's all for today. In the next video, we'll be doing question 5, 6, and question 7 for those, for everyone, right? That's all.